that result. But maybe we end up getting immersed in discussion. It's not the end of the world if I don't manage to write all the details of that end result on the board. And yeah, following up on my disclaimer, this talk is taking a rather personal view on the subject of string perturbation theory. I'll be quite hungry for explicit formula for string scattering amplitudes. So I will give an overview of which kind of string amplitudes are evaluated to the extent that you can get numbers out of them, order by order in an alpha prime expansion. So before even mentioning any explicit results, I should formulate the wish list taken in this talk, at which point I consider a specific amplitude as ready for low energy expansion. The disclaimer number one, I will only do massless external states. Of course, the string spectrum has an infinite tower of massive states whose scattering is exciting as well. And I very much enjoyed collaborating with Renan and Max and Henrik last year to get some all multiplicity results for tree-level amplitudes involving a massive state. But for today, all the external states are going to be massless. And I will present amplitudes in a form that you can go flexibly in between type 1 and type 2. And in principle, also heterotic string theories. So whenever you're not sure, think of the external states as being gauge or gravity multiplets. Good. But as I was alluding to before, I want to have simplified expressions for the string amplitudes of these states, which are amenable to low energy expansions. Because one of the motivations for string amplitudes is to stress test string dualities or to maybe infer new symmetries between or within individual theories. So it's quite nice if you can be arbitrarily explicit at a given order in alpha prime and even get out a number if you wish, if you send the external momenta and polarizations to numbers. And if this is the goal, then you should really simplify the conventional prescriptions a lot, in the sense that you may have to evaluate a CFT correlator with picture changing operators or B-ghosts, which depend on spurious variables, where it doesn't matter where you insert the PCO or where you insert the B-ghost. Of course, we usually know from the formalism that we are not depending on the locations of PCOs and B-ghosts, but still, it can be hard work to simplify the amplitudes to the extent that these locations drop out. So one of the criteria is that you don't see any spurious locations of PCOs or B-ghosts in the simplified expressions. All right. So having made all of these disclaimers, maybe we can take a first look at what kind of amplitudes are known up to date in a simplified form or in a way that you can extract low energy expansions. So here, this is the overview of 4-point scattering amplitudes. So maybe I need yet another piece of board to tell you that all of this is 4 points. So what do we have at the 4-point level? Well, the very old result at tree level is due to Veneziano and Virasoro-Shapiro. Maybe these are the 4-point functions that triggered the birth of string theory, where at tree level with 4 external massless states, we have ratios of gamma functions, or in the open string case, the Euler beta function, which was highlighted by Veneziano, among other things, for its crossing symmetry properties. So 4-point tree level is a pretty old result. And if you now look at the years where loop amplitudes with 4 external states were firstly computed, you see that it usually takes a decade and more to go from one loop order to the next. And Not sure whether I had this in the disclaimers. I'm here looking at superstring amplitudes as opposed to bosonic string amplitudes. It may well be the case that the bosonic string allows you to write more general multi-loop, multi-leg results, but here I'm specifically after the superstring, where on the positive note, you have space-time supersymmetry on your side, or sometimes also worldsheet supersymmetry, but also you need to think about how you realize all these simplifying features. And in the RNS formalism, this gives you some challenges to deal with supermoduli on a super Riemann surfaces. And in the pure spinor formalism, there are other challenges at sufficiently high loop order, such as tentative divergences in the zero modes of the ghost variables, where you have to do something. So this is just a small sample of circumstances that are responsible for not having a for loop and beyond result in this table so far. But yeah, let's talk about the things that we have. One loop 4 points done in 82 by Brink, Green, and Schwartz, including the low energy limit. And yeah, one of the aside results was a big wow for the supergravity community. As a corollary of the 4.1 loop amplitude, as I will detail later on, we see that 4-point loop integrals in super Yang-Mills and supergravity are extremely simple and only involve the box graph. And I will make analogous statements about the simplifying features of 2-loop amplitudes in field theory that you get almost as a side gift once you have done a good job on the respective string amplitude. Yeah, let's get to the 2-loop results. So here the golden year was 2005, starting with the RNS evaluation of Doker and Fong for external Neveu-Schwarz states. And in the very same year, in fact, just 2 months thereafter, Nathan presented a 2-loop 4-point function in pure spinor superspace, which also delivered the fermionic or Raman sector components. And in the team of Nathan and Carlos Mafra, it was shown again in 2005 that these pure spinor expressions are consistent with the RNS results for external RNS states. Well, in fact, they match, yeah. Good, so this is about 2-loop 4 points. And now at 3 loops, we have a highly heroic calculation from 2013. I guess Humberto is in the audience, or is also Carlos in perhaps? Yeah. Okay, so a big respect to Humberto and Carlos for having evaluated 3-loop 4 points in the low energy limit. So they looked specifically at the order of e to the 6, r to the 4, the leading order in alpha prime for the analytic contributions, because this expression, including its normalization, was quite important for S duality of type 2B superstrings. And Carlos and Humberto succeeded to show that this low energy limit is exactly what an S duality prediction of Green and Van Hoof required. Yeah, so mission clearly accomplished for their low energy limit project. And just last year, there was a proposal how to uplift the result of Humberto and Carlos to all orders in alpha prime, going beyond the low energy limit. Yeah, where Yvonne Geyer and Ricardo Montero, as well as Ricardo Muchao-Stark, wrote down bosonic moduli space integrals, which give that low energy limit, and yeah, which are furthermore claimed to entail all the alpha prime corrections. And they used a very inspiring mix of ambitwister methods and input from the field theory limit, namely the Bern-Carrasco-Johansson representation of 3-loop super Yang-Mills and supergravity amplitudes. So that's a wonderful showcase of how different toolboxes can nicely work together to make progress on the multi-loop frontier. Given that also 4-loop and 5-loop amplitudes in field theory are known from Bern-Carrasco-Johansson and others, it wouldn't surprise me if a lot of information can also be transferred to the respective superstring amplitudes. Yeah, so this is a list of 4-point achievements, but I already alluded to a 5-point result, which I may or may not have the time to present. So at 2-loop 5 points, the history of successful evaluations started with collaboration between Humberto Carlos and myself in 2015, where we evaluated the low energy limit and again showed consistency with S-duality expectations. And yeah, similar situation as in this field, we presented the low energy limit. So there was the question in the air, what's happening at higher orders in alpha prime? And yeah, the three references I gave at the beginning of the talk are delivering this gap. So this is the triplet of papers that I mentioned together with Eric Doker, Carlos Mafra, and Piolin. Triplet of papers dating back to 2020 and 2021. All right, and just for completeness, 5-point functions at lower loop orders were studied in various corners of the literature. So for instance, one loop 5 points was attacked in the Green-Schwarz formalism by David Richards in 2008. And there's external bosons here. And for superspace purposes, there is a result by Michael Green, Carlos, and myself from 2013, where you can get superspace expressions for one loop 5 points, and where also some orders in the low energy expansion were explored and compared with S-duality expectations. And for higher points, let me not get too excessive in the details. At tree level, there is all n result, like a simplified form of n-point tree level amplitudes due to work I did in 2011 with Carlos Mafra and Stefan Stieberger. So here, all n-point tree-level amplitudes of the open superstring are simplified to a basis of genus 0 integrals. And the kinematic factors were all conspiring to field theory building blocks. So it's nice to disentangle the polarization tensors from scalar integrals that capture the alpha prime corrections. So you completely decouple the problem of figuring out the superspace structure from the mathematical problem of getting the integrals expanded. For sure, there's a lot to be said about the mathematics of these alpha prime corrections, and it's quite assuring to have all of them in scalar integrals over the respective modular space, decoupled from the superfield structure. And yeah, this is also the goal for all other fields in this array, to get all the alpha prime dynamics, all the infinite series in alpha prime into scalar quantities that decouple as much as possible from the superfields. There are restrictions to that at loop level, because there is an issue with loop momenta that I will get back to later on. But the general philosophy stays the same, that you should decouple the alpha prime dependence as much as you can from the superspace structure. All right, so for one loop, there are also a couple of higher point results. In fact, some all multiplicity partial results from the 80s due to Tsuchiya, who looked at the sum over spin structures in the RNS formalism. So the RNS formalism is known for not manifesting all the space-time supersymmetries, but you find them as you sum over the different spin structures of the worldsheet spinners. And already in, not sure whether it was 87, 88, or 89, Tsuchiya succeeded to devise a method to evaluate the n-point sums over spin structures. So if you want to have access to the n-gluon amplitude with all the supersymmetry cancellations manifested, you can dig up Tsuchiya's results. And this was also quite valuable in recent years to learn about the connection to elliptic integrals, and specifically elliptic polylogarithms. So in order to get the Neveu-Schwarz sector results, maybe not in an integral basis, but at least with the RNS spin sums carried out, you can already look there. But of course, it was a big topic of recent research to get these expressions uplifted to superspace. And there I can give you in private chat some specific pointers to work with Carlos Mafra over the recent years, where we presented superspace uplifts, namely one loop amplitudes at 6 point and 7 points, computed from pure spinor building blocks, which also address the external fermions or Ramond sector states. Good. So this is a rough overview of what has been done, and maybe it looks, maybe it raises the question why the hell I'm going for all these multi-loop and multi-leg exercises. So as the next part of the talk, I owe you some elements of motivation, why it is rewarding to study string amplitudes and to evaluate them in the detailed fashion that I advertised at the beginning of the talk. Yeah, before I go to this motivational part of the talk, is there any immediate question on this? Okay, then we are done with the status report. And let's now go to the question, why string amplitudes and why go for large loop orders or large leg orders? So just to be clear, little n is always the number of external states. I'm not talking about a large n limit a la n equal 4 super Young-Mills. So for me, the number of colors is always finite. Okay, there are roughly 4 lines of motivation that I want to mention, though I won't do justice to many other additional motivation elements. So one of the spin-offs that I already alluded to before is that you learn a lot about field theories. Specifically, you learn about the supergravity and super Young-Mills amplitudes obtained from the alpha prime to 0. So if you do this for type 2 superstring amplitudes, then you get from the field theory limit the maximal supergravity. Choosing a diplomatic wording with maximal supergravity, I mean the theories with 32 supercharges in your favorite space-time dimensionality. Well, in the first place, the type 2 superstring clearly lives in 10 dimensions, but you can compactify on a torus without breaking any supersymmetries, and you can still learn about lower dimensional supergravity from that compactified type 2 results. Because the kinds of partition functions that you introduce by compactifying on the torus, they affect the loop integrands in maximal supergravity in a rather minimally invasive way. So just to finish that line, it's the loop integrands of maximal supergravity that can be conveniently studied from strings. Of course, I should be careful to make an integral statement, for instance, because type 2 superstring amplitudes are UV finite, but maximal supergravity is clearly not UV finite in sufficiently high dimensions. Well, simplest example is at one loop, where the UV critical dimension here is d equal 8. So with the 10 dimensions of the uncompactified type 2 superstring, you're already out of bounds. So in a certain sense, you don't compute the actual loop integrand of supergravity, but a UV regulated version by taking this field theory limit or point particle limit. But regardless on loop integration issues, you can learn a lot about the structure of these supergravity loop integrands. And the thing I want to highlight is the BCJ double copy thing. In the sense that the kinematic building blocks, aka numerators of supergravity loop integrands, can be assembled from squares of super Young-Mills quantities. So the kinematic ingredients in supergravity loop integrands, as I was saying, come in a loose sense from the square of super Young-Mills, which is an informal way of saying work out the corresponding loop integrands in super Young-Mills theory and square the numerators if you have a preferred cubic diagram representation. So the fine print is that you need to realize color kinematics duality in the parametrization of the super Young-Mills loop integrand, but also for this you get help from the string. So in a variety of examples, the color kinematics duality here was manifested by the field theory limit of the superstring. So the highest result where this was done is the 2-loop 5-point amplitudes I mentioned before. Good. This is motivation number 1. In summary, color kinematics in gauge theory and BCJ double copy for perturbative gravity comes quite often as a corollary of string amplitudes, with a very systematic understanding at tree level, partial results at 1 loop, complete results if you're happy with linearized Feynman propagators, and partial results at 2 loop, with hopefully more to come. All right, I hope you're with me for this field theory line of motivation. And now the next point of motivation is about the full-fledged string amplitude, including its alpha prime decoration, including higher orders in the low energy expansion. So low energy expansion, as I alluded to before, is nicely cross-fertilizing with string dualities. There's less work on the heterotic type 1 duality with perturbative manifestations, and there's more literature on the self-duality of type 2b superstrings. So the most frequent example is the S-duality of the type 2b theory, which is, loosely speaking, a strong recoupling duality acting on the axiodilaton field. The dilaton, as you know, sets the string coupling, and S-duality is in fact a modular invariance with respect to the complex axiodilaton field in the type 2b theory. Okay, and this S-duality, it, among other things, relates different orders in perturbation theory. If S-duality is meant to hold order by order in alpha prime, then there should be a lot of parallels between, say, tree level, 1 loop, 2 loop, and higher loop amplitudes. So an essential part of the business is to really convince ourselves that our higher loop string amplitudes fit together with the tree level results. So this has already been done a while ago at 4 points. And here is now a specific selling point to also look at this at 5 points. Namely, there are a couple of processes that do not exist at 4 points. So 5 points is the first time where you can violate the U1 R symmetry of the supergravity field. The type 2b supergravity has a U1 R symmetry where the axiodilaton is the highest weight state and the complex conjugate axiodilaton is the lowest weight state. And supergravity asks you to always preserve R symmetry in each amplitude. So don't even think about scattering 4 gravitons with an external axiodilaton. That's not compatible with the R symmetry of supergravity. But the strings are relatively unconstrained. String amplitudes at 5 points and beyond can break that R symmetry. And these are amusingly simple expressions, say specifically 4 gravitons and 1 axiodilaton, which is contained in these results. It's one of these infamous R symmetry violating amplitudes. And S-duality has a lot to say about how U1 violating amplitudes relate to the conserving ones. So it has to do with modular functions versus modular forms. So in a nutshell, the axiodilaton transforms under the S duality SL2Z, and therefore the coefficients of S duality, the coefficients of U1 violating couplings have to be modular forms of non-trivial weight. So all this to say, 5-point amplitudes are mandatory if you want to have a door into the U1 violating universe within the string amplitudes. And yeah, it again has specific predictions how the tree-level results are related to one loop and two loop. There are very precise predictions of S duality in presence of U1 violation. And all of these predictions were confirmed to the alpha prime orders we could access in these papers. Also, 5 points gives you examples of new operators, which you don't see at the 4-point level. So already at tree level, you only have Riemann zetas in the low energy expansions here, but you get multiple zeta values in the low energy expansions there. And in S duality, there must be a very prominent role for the multiple zeta values. Namely, there will be certain zero modes of more general modular functions and modular forms that nobody has constructed so far. So this is another instance where the exploration of higher multiplicity amplitudes point out new features and structures in string perturbation theory. And there is a lot of upcoming homework for us to explore these couplings that come with multi-zetas and to relate tree-level, one-loop, two-loop results, and to get a glimpse of the modular functions of the axiodilaton field that come along with these interactions. Good, this is to give a flavor of the S duality motivation to study string scattering amplitudes. And maybe I already made the transition to the third motivation line for multi-loop, multi-leg string amplitudes, namely the mathematical structures of them. There was already the buzzword of multiple zeta values and modular functions, modular forms in the air. And there has been a lot of crosstalk recently between string perturbation theory and pure mathematics, specifically with number theory and algebraic geometry. So to make a somewhat generic statement how these things come about, for sure your goal in evaluating a string amplitude is to integrate over all the moduli. Put n punctures on a genus G surface and integrate over the moduli space of these genus G surfaces, say the period matrix in the simplest case, or more generally the complex structure module. But what if you only do a subset of that task? What if you only integrate over the vertex positions, over the punctures or marked points? And you keep the surface fixed. You work at fixed complex structure moduli, collectively denoted by omega. So this will give rise to modular forms. With respect to the modular group at genus G, sp2g, z, which acts on omega. And here with the d square vertex positions, I'm secretly placing myself on the closed string side, where left movers bring meromorphic functions, right movers bring anti-meromorphic functions. So specifically, the closed string amplitudes serve as a factory of non-holomorphic modular forms. And I hope I don't sound too pedantic in stressing that. Think of modular forms at genus 1. As long as things are holomorphic, you just need the Eisenstein series G4 and G6, and all the rest is generated by the ring, by polynomials in G4 and G6. So even if holomorphic modular forms are pretty constrained, you open a completely new space by allowing non-holomorphicity. So already at genus 1, there is an infinite class of non-holomorphic modular forms generated by integration over torus punctures. So in this genus 1 setting, fix the modular parameter tau, which encodes the shape of the torus, integrate over all the punctures sitting on that torus, and the resulting objects have been dubbed modular graph forms. And they were really unheard of in mathematics at the time when the first examples and results came out. So pioneering work goes all the way back to 1999 of Green and Van Hoof. And later, the systematic introduction was in papers Green, Van Hoof, Doker, Gurdogan, or a separate paper, Doker, Green, to introduce the forms on top of the modular functions. And yeah, here it's the alpha prime expansion that gives rise to a generating series. So each order in alpha prime offers a different representative, offers different members of this infinite space of these modular graph forms. So that's a highly exciting connection with number theory, algebraic geometry, objects that have firstly been seen in closed string amplitude calculations. And we haven't even finished integrating over the moduli and obtain such rich structures here. Of course, studying the properties of modular graph forms is also instrumental to finish the job and to also integrate over tau and omega. For sure, this is highly supportive to also connect with S-duality. But even before doing the final integration, there is a lot of data to unpack, structures to be encountered. And also at higher genus, there will be infinite families of such modular graph forms, or as Eric, Doka, and myself recently proposed, generalizations to tensors of sp2g, z. Yeah, so this is motivation number 3, why it makes sense to spend a lot of time and energy on multi-particle and multi-loop string amplitudes. And a 4th line of motivation, maybe I'll just go through this schematically. Also at the technical level, there are a lot of synergies between different cells here. So the details depend on the formalism, but let's assume you are also a pure spinor practitioner and look at the calculations at 2 loop 5 points. Then you find that the pure spinor computation is very much guided by zero modes, mostly the fermionic zero modes, but you can also afford to pick up a bosonic zero mode. So there's a very specific zero mode pattern characterizing the 2 loop 5 point calculation. And at 3 loop 4 points, there is similar freedom in the zero mode saturation pattern, in the sense that also here, Humberto and Carlos could pick up to 1 bosonic zero mode. So all this to say, the flow of the zero mode saturation is very similar at 2 loop 5 points and 3 loop 4 points. So in that case, the history was that this result came first, but regardless on what is first, what is second, there are synergies. By doing higher loops, you learn more about the zero mode patterns at higher points and possibly lower loop. And conversely, if you keep on going for 2 loop 6 point, 7 point, n points, then you meet zero mode saturation patterns that will be helpful for you at higher loop 4 points. Yeah, so in a very loose sense, you can trade loops for legs if you look for equivalence classes of zero mode saturation patterns. I admit this is a bit oversimplified, but the more experience you have there, the easier your time will be to go into the other direction, the multi-loop and multi-leg plot. All right, now I believe I'm done with the words of motivation. And if there's no urgent question right now, I will go into some detailed 4-point examples at 1 loop and 2 loops. And of course, shout whenever the writing is not readable, whether I should speak louder. Or, yeah. Let's come to the technical half of the talk. And my goal is to explain the techniques that were instrumental to get a two-loop 5-point function at all energies. And in order to get closer to that, I shall review 4-point amplitudes at 1 loop and 2 loops, and use these examples to motivate the notion of chiral splitting, how you can ensure that the closed string moduli space integrand is the square of an open string calculation. Okay, so let's go through the review of the 1 loop result. As I said, it was firstly done by Green-Schwarz-Brink for external Neveu-Schwarz states. And I think the pure spinor calculation was done by Nathan in 2004, presenting the completion to all combinations of Neveu-Schwarz and Ramon. Good, so this 1 loop 4-point amplitude allows you to get rid of all the polarization dependence before you even touch the alpha primes. So there is a kinematic factor that you can pull out. If you do external Neveu-Schwarz states, then we have linearized field strengths here. So the conventions are that these F's are the curl of polarization vectors. H invariant as a at a linearized level, and T8 is a specific 8 index tensor to contract 4 of these F's for the 4 external states. And here, on the one hand, I'm trying to serve you a graviton amplitude, but on the other hand, you see a polarization vector that looks like a gauge boson. So here is the absolute value square, which just means you double copy everything in here, where you use a different epsilon on the other side. So you can later on grab the graviton, the B field, and the dilaton. So this is just to recap for you how these double copy constructions work. If you know the open string ingredient T8, then you're automatically getting the type 2 supergravity components by doubling all that. And it's well known how to supersymmetrize. I can also give you the pure spinor representation if you like. Good, so this is the kinematic part, which doesn't really worry about alpha prime dependence. And let's now get to a specific instance of the modular space integral. So we are dealing with a torus worldsheet, which is characterized by a complex structure modulus tau. And the inequivalent tori under the modular group had a tau parameter in the upper half plane, or more precisely in the keyhole region, which is a subspace of the upper half plane. So make sure you only integrate over the keyhole region F, and then you have touched upon all the inequivalent tori. So now it's time to integrate over the punctures. So by translation invariance on the torus, you can decide that one of the punctures is wherever you like. So maybe we choose to set the first puncture to be at the origin, and then the leftover integrations are over Z2, Z3, and Z4. And maybe you are wondering why I'm so pedantic about where to put the inverse in taus. So the habit here is to have modular invariant constituents. So both this integration measure and that integration measure are separately modular invariant. Okay, and here are 3 copies of the torus that you integrate over. Good, now what's the integrand? Well, part of the moduli space integrand are already pulled out. And maybe one of the nice consequences of space-time supersymmetry is that The only z or tau dependence in the integrand is the so-called Cobra-Nielsen factor. So this is worth defining for all loop and leg orders. So whenever I informally write Kn, then this refers endpoints in genus G. This refers to an exponential over all pairs of Green's functions. No, sorry, over Green's functions involving all pairs of vertex insertion points Z. And yeah, this just comes out of a correlation function on a genus G surface involving the plane waves, the e to the I kx parts of the vertex operators. And yeah, if you look at the fine print, then there is a dimensionless Mandelstam invariant coming here. So whenever I loosely refer to an alpha prime expansion, what I truly meant was simultaneous Laurent expansion in all of these dimensionless Mandelstam invariants. Yeah, so here in the specific one loop 4-point instance, the Cobra-Nielsen factor is all there is. And maybe I can briefly remind you of the non-holomorphic modular forms that I mentioned. If you just close your eyes and Taylor expand the exponential, then you end up integrating Green's functions. And you can also engineer the Green's function to be modular invariant. Then, given that also the integration measures are modular invariant, this you can take as a factory for non-holomorphic modular forms with as many Green's functions as you wish. And this also introduces transcendental weight any way you like. But let's get back to the physics of this 4-point amplitude for gravitons in type 2b theories. As I said, the Cobra-Nielsen factor is all there is. So let me just highlight that there are no singularities whatsoever as the punctures collide. And this is quite crucial for the field theory limit. If you take alpha prime to 0, then you receive the box graph. So the corollary as alpha prime goes to 0 is that the 4-point one loop amplitude and maximal supergravity is only the box graph and nothing else. This was clearly out of reach to field theory amplitude methods in that year. And the remarkable thing is that no triangle and bubble graphs arise. So you could have expected, just by brainstorming about Feynman graphs, that this supergravity loop integrand could also contain graphs like this. And well, in principle, they could be generated by string theory, but they would require some additional singularities here. So the absence of these singularities is the root of the no triangle properties. To make sure that this blackboard picture is not getting confusing, I better wipe out all the things which are not there. So given that there's nothing else, no more singularities accompanying the Cobra-Nielsen factor, there is no chance for a bubble graph, there is no chance for a triangle graph, and we can lean back to study the box graph only. Yeah. So this is a showcase where the supersymmetry cancellations in field theory have a nice stringy origin. So here, the stringy origin is to simplify the correlator to the extent that you see that the H can be pulled out and that there are no singularities next door to the Cobra-Nielsen factor. And the pure spinor formalism gives you another way to see these supersymmetry cancellations. Namely, you are so busy saturating the fermionic zero modes that you can't put any further singularities in here. So no matter which formalism you use, there are different ways to see the space-time supersymmetry in action on the string theory side and in the field theory limit as well. Any further question on one loop 4 points? Okay, after 1 comes 2, let's look at the 2-loop 4-point amplitudes in a similar way. So this is to review the 2-loop results obtained by Do-Ka-Fong in the RNS formalism for external Oliver-Schwartz states and obtained in the pure spinor formalism for the respective supermultiplets by Berkowitz-Mafra. And to begin with, there are again good news about the polarizations, that they are again sitting in the double copy of T8 plus the same fermionic completion as before. Okay, so once more, you can get rid of all the polarizations up front, and you are left with all the alpha primes sitting in a scalar integral. And yeah, that scalar integral, it starts with the higher genus uplift of the d squared tau integral. So now at genus 2, you have 3 complex structure moduli that you can package into a 2x2 period matrix omega. And there is some analog of the keyhole region known as the Siegel upper half space that you need to integrate over. So this is the moduli space of compact genus 2 Riemann surfaces. And yeah, given that there are 3 complex period matrix entries, it's a 6-dimensional integral if you count the real variables for the real parts and imaginary parts. Okay, now in the next line, I'm writing down the integrations over the surface. So now it's the genus 2 surface at fixed complex structure moduli omega. And now I'm supposed to write the dz's and dz bars. But here comes a new feature. There is more than one dz at genus 2. So I need to make a few comments what it means to do d square z beyond genus 1. So to be precise, if you are a genus G, there is a G component vector of holomorphic differentials. Holomorphic or abelian differentials. So for both the meromorphic and for the anti-meromorphic part, you need an omega with an index, yeah, for both z and z bar. So at first glance, it looks like this is an 8-index tensor for 4 variables coming with a omega I and a complex conjugate omega j. But again, supersymmetry helps. Thanks to maximal spacetime supersymmetry, we only get an antisymmetric combination of these omegas. So let's introduce an object delta, which is the antisymmetrized way of combining the omega 1 and omega 2s in vertices ZA and ZB. Okay. So this is one form in both ZA and ZB, more precisely a holomorphic 1, 0. And if we once more take a holomorphic square, then this has the right form degree to be integrated over 4 copies of the surface. Okay, now it's time to spell out the detailed dependence on these objects delta. They come decorated with Mandelstam variables. And it's in fact a permutation invariant. This may not be manifest in the way I write it, but yeah, there's a permutation symmetric combination of delta delta and 2 powers of momentum. And all of this absolute value squared. And finally, here's my obsession to make things term by term modular invariant. Okay, so there are a lot of nice consequences of this structure. One is you have at least 4 momenta after completing the holomorphic square. So this means the low energy limit already has a huge number of derivatives, namely it's a low energy limit d to the 4th, r to the 4th, if you interpret this as a linearized Riemann curvature here. And the second nice consequence of that result is that, again, the field theory limit is very picky. So you can again ask what kind of Feynman graphs arise, alpha prime goes to 0. What is the prediction for the loop integrand in supergravity and super Yang-Mills? So there is just a simple arrangement of double boxes. Maybe the natural continuation of this box graph expression in one loop. But also there is a non-planar version. Not sure whether I'm drawing this in a particularly pretty way, but this is an attempt to draw a non-planar analog of this double box. So again, there's a huge list of Feynman graphs that do not arise in the field theory limit. So clearly there are no triangles out there. You could in principle imagine such a graph, but this would require some more singularities here. Oh, by the way, I forgot the Cobra-Nielsen factor. There's again the usual exponential of Green's functions here. Sorry about that. Yeah. Oh, I'm sorry, and I drew the wrong graph. Confusion on 2 ends. I was just explaining that this triangle containing graph does not arise because we don't have the required short distance singularities to generate that tree-level propagators. So the absence of this diagram is easier to see, but I wanted to highlight a more subtle cancellation. So this is now the diagram that I just erased. So why not contemplate this combination of a pentagon and a triangle graph? It doesn't have any dangling trees. So the absence of short distance singularities here doesn't tell you by itself whether or not this graph arises. But this graph is incompatible with these delta-delta objects. So given that all the differentials conspire to 2 copies of that delta, this is the origin of, well, no penta triangle. So here at 2 loops, it's a slightly more refined story, how the properties of the stringy loop integrand, moduli space integrand, tells you about the absence of certain graphs. Yeah, this is what I wanted to say about 2 loop 4 points. I don't hear much. I hope that everything is all right about.
No, we're here.
Okay, good. Yeah, here in these 2-point showcases, we were very lucky that all the polarization went out from the beginning and that the closed string polarizations are clean double copies. And this is a bit a luxury phenomenon at 4 points, but you won't get that on the nose for 5 points. So as an interlude, I want to remind you of chiral splitting, how to ensure that also for endpoints, the closed string moduli space integrand has a double copy structure. So this is essentially a recycling trick to reduce the simplification of the CFT correlator to an open string problem, but it has vast conceptual implications for gravity being a double copy. So what I'm reviewing here is chiral splitting due to Okafong from the late 80s. And in a certain sense, this is the cradle of the gravitational double copy, while also loop integrands in supergravity theories can be assembled from suitable squares of kinematic numerators in super Yang-Mills. What is this about? So the name of the game is to decouple the left and right movers as far as you can. And at genus 0, you have no trouble at all. They decouple on their own, the left and right movers. So if you have any obstructions to decoupling the left and right movers, you need to be at loop level. And it is more specifically through bosonic zero modes. Let me be specific. The zero modes that couple left and right movers in the first place, these are zero modes of the worldsheet derivative of the free boson. And by zero mode, I mean an integral over an A cycle of the surface. So this, as you can see, is camouflaging the modular invariance. So this is one of the many situations where you can't have it all manifest at the same time. If you want to see the closed string integrand as a double copy, then you will have to live with a singling out of the A cycles in intermediate steps. But this is, of course, no obstruction to manifesting modular invariance later as you integrate over the loop momentum. Yeah, so here with this picture, I wanted to just set the terminology or notation. Choose your A cycles on the surface. Each A cycle gives rise to a different zero mode and to a different loop momentum. And the reason I'm writing this formula is that at the level of these zero modes, the left and right movers couple. So the loop momentum from the viewpoint of the left movers, the holomorphic derivative, is minus the loop momentum from the viewpoint of the right movers with anti-holomorphic derivative. This is the coupling between left and right movers that I'm warning about. And the way to deal with it, it may look very, very simple. Well, it actually is very simple. So if only one mode in the path integral is obstructing a factorization of left and right movers, then you should outsource that from the path integral and take care of the loop integral later. So the finite sector of the path integral is over the 10G zero modes here. 10 for the space-time dimensions and G for the genus, because this is counting the A cycles. So it's this loop integral that you're asked to outsource from the path integral if you do chiral splitting. Instead of integrating over all the modes, 0 and 1, 0 of the free boson and the other fields, you leave out that finite dimensional integral for the end. Okay, and yeah, the reward for this, at fixed loop momentum, the closed string moduli space integrand is on the nose a double copy of open string building blocks. So I hope there's enough ammunition in these whiteboard markers. Is this still visible?
I can see it, but not very well.
Oh, not very well is not enough. Then let's better go to elsewhere. So as a reward for working at fixed loop momentum, you get a honest to God factorization of the closed string correlators, or at least the building blocks that capture the path integral over infinitely many modes. So the promised effect of chiral splitting is that closed string integrands factorize at fixed loop momenta into a square of so-called chiral amplitudes. So the chiral amplitudes at genus G for n points will be functions only of the left moving polarizations, epsilon, and not on the epsilon twill. So this is, if you wish, an open string quantity with half the complexity of the polarization dependence. And for sure, these chiral amplitudes will depend on the external momenta, like you saw it in the T8 tensor, but also they will depend on the loop momenta, which we reserved for the last later integration. And as for correlators without chiral splitting, they of course depend on the moduli, the punctures and the complex structure moduli of the surface. And the clue is that they are depending meromorphically on the z's and omegas. So since later on you do an absolute value sphere, you get all the anti-meromorphic dependence from the second half. Okay, on the risk of being a little bit too abstract here, maybe I should just spell out the specific realization. So if you follow this chiral splitting prescription, then for instance, at two loops, you get your closed string amplitudes in the following form. Say you do the two loop endpoint function, the specific 5-point result will come hopefully in a few minutes. Then you integrate over 20 zero modes, 20 loop momenta. And here is the same Siegel upper half space that I mentioned before for the 2x2 period matrices with complex entries. And here comes the heart of chiral splitting. In the endpoint function, there are n copies of the surface to be integrated over. I'm lazy and suppress the polarization and momentum dependence. And as I advertised before, the problem reduces to computing a meromorphic open string quantity, the chiral amplitude f, and then the second open string half comes from the complex conjugate. And this is the expression or the structure of the type 2 amplitudes, where we have the left and right movers on symmetric footing. Maybe we need to adjust the chiralities of the fermions, but as a defining property of the type 2 theory, we are symmetric. We have the same amount of supersymmetries for the left and the right movers. But with chiral splitting, you are even more flexible than that. If you are brave enough to have computed the bosonic chiral amplitude, pretending you are doing an open bosonic string calculation in genus 2, then you can also get the heterotic string amplitude at genus 2. That's another selling point of chiral splitting. Once you have the supersymmetric chiral half in your pocket, it's completely up to you whether you want to use this for a type 1 calculation, where you impose some boundary conditions on open string endpoints, or whether you do a symmetric double copy to do type 2 amplitudes, or whether you do this asymmetric double copy to do heterotic strings. It's the same chiral amplitude on the supersymmetric side. So it really pays off to think about getting this object into good shape. I should line up this general statement with the 4-point example we just went through. How does the 4-point two-loop amplitude, which I just reviewed, how does it line up with chiral splitting, and what's the 4-point example of the chiral amplitude. So in the above 4-point case, first of all, there is again a Cobra-Nielsen factor that goes out. And well, ideally, I would be telling you that you take the square root of the Cobra-Nielsen factor, but this would be oversimplified. The truth is that you get a certain chiral version of the Cobra-Nielsen factor, which I should spell out on a second. So this is chiral Cobra-Nielsen. And it can be swiftly written down for all genera and endpoints. It is another huge exponential. And let's start with the alpha primes. So here, this is pretty similar to the closed string Green's functions that I told you about before. But the closed string Green's function is usually not at all meromorphic. But here I'm supposed to present you a meromorphic quantity. And the way to go is to use the prime form, capital E. So the prime form is characterized by short distance singular behavior like Zi minus Zj. And you can construct it from odd Jacobi theta functions. Okay, so this is, if you wish, the chiral splitting antecedent of the closed string Green's function. But the closed string Green's function is engineered to be doubly periodic. And there's a doubly periodic polynomial term with im-z's for the experts. And to get this doubly periodic term, you need to know about the loop momentum dependence of the chiral Cobra-Nielsen factor. So here we have the dot products of internal and external momenta. And we have these zeta coordinates on the Jacobian variety. Sorry about all that name dropping. So this is the integrals of the abelian differentials from some reference point all the way to the point Zj. Okay, and finally, there is a moduli dependent term with the period matrices, namely dot products of loop momenta contracted with the period matrix entries. Whew, now we are done. Okay, so at first glance, it might look unpleasant that the loop momentum is all over the place, but in fact, it's on the way of giving you a Gaussian integral. I mean, even if you take the absolute value square of this, you have the loop momentum in a Gaussian integral. That's not at all scary. You can just do the Gaussian integral if there are no more loop momenta coming here. And indeed, at 4 points, there is no further loop momentum dependence on the chiral amplitude, apart from this Cobra-Nielsen factor, which is universal and super easy to predict. All the rest is independent on the loop momentum. So here is the T8 tensor that you saw before. And here comes the differential structure. After all, I need to present you a holomorphic 4 form, which you can integrate over 4 copies of the surface. And this is the same combination with external momenta that you have seen before. All right. Yeah, so this is repackaging the 4-point amplitude from before, now embedded in the chiral splitting formalism. And this will give me an easy time to write down the 5-point generalization. maybe two general remarks about chiral splitting. First of all, at the loop orders where we have all of RNS and pure spinor computations under control, yeah, this is completely agnostic to which formalism you use. I mean, this free boson XM on the worldsheet, it's there in Ammoneve-Schwarz, it's there in Green-Schwarz, it's there in pure spinor superstrings. So chiral splitting works exactly the same way. So you can flexibly go back and forth in between the formalisms. It's the same recipe. Then for higher loop orders where we don't yet have control, where RNS keeps us busy with supermoduli and their tentative non-splitness, where pure spinors have challenges with the regularization of zero mode divergences for the ghost variables. In those cases, I don't know of a general proof that chiral splitting necessarily goes through, or there can indeed be issues that challenge chiral splitting. So the scope of these formula is understood to apply to those string amplitudes where you're not yet overwhelmed by these bigger, higher loop problems. All right, that brings me to the end of chiral splitting review, plus a 4-point example. And I will now proceed to presenting the 5-point result, or more precisely, the chiral amplitude for that. Any questions before I do that?
I have a question.
Yeah, please go ahead.
So at high loops, what part of the chiral splitting prescription would be expected to break down?
Okay, I'm definitely not an expert. Let's say what many practitioners dream of is to get rid of all the fermionic moduli integrations, integrating out fermionic moduli first and going down to a purely bosonic moduli space integral. And it's not clear whether or not this can be done while preserving meromorphicity. I think the challenge is about a holomorphic projection down to ordinary moduli space. And I think there is work out there which pinpoints specific obstructions.
Yeah. For example, one might expect that the Cobra Nielsen factor actually remains correct, whereas the coefficient then loses the meromorphicity, the chiral splitness.
Oh yeah, I think, yeah, I agree with you there. Cobra Nielsen factor is safe. This is the good old free boson. This is treated already in the bosonic string. Indeed, this has no issues whatsoever for arbitrary G and N. Yeah, if there is a problem, then it's in the fermionic variables, the worldsheet spinors, and these are, as you say, the decorations. What else is there, the chiral amplitude, besides the Cobra Nielsen factor?
Yeah.
Fully with you. Yeah.
Okay, thanks. Yeah.
All right, let's do 5 points. Now that we got back to the ubiquitous Cobra Nielsen factor and its robustness in the multi-loop, let me focus on the 5-point chiral amplitude modulo Cobra Nielsen. Because this we know anyway is around. And again, this is about the triplet of papers I mentioned at the beginning with Eric, Carlos, and Boris. And the goal was to find an all-energy expression that generalizes the low energy limit computed in 2015 with Humberto and Carlos. Okay, so I guess I will just go ahead and write out the expression for the chiral amplitude. And as we go along, I will explain some of its ingredients. So the 4-point function had this funny differential structure where these deltas were accompanied by Mandelstam invariants. And even though I just wrote down 2 terms, it was permutation invariant. And the same you can do at 5 points, possibly even higher points. You can write down a very economic expression like this 5-term cyclic orbit, and you already have a permutation invariant, even though this is not manifest. It has to do with various fields type identities if you change the entries here. So a large part of this chiral amplitude is addressing with deltas and Mandelstams of a simpler quantity. And that simpler quantity, privately, I think about this as the one loop chiral amplitude. Imagine you were doing 5-point scattering at one loop, then you get the chiral amplitude, which is almost the one I will write down here. So I want to convey the idea that a huge part of the 2-loop answer is a minimal dressing of the 1-loop answer. And this is what we experienced at 4 points. We had the T8 tensor going up front in both cases, and 2 loops additionally had these delta delta in the chiral amplitude. And yeah, the same is true at 5 points for parts of the answer. There are T8 tensors now filled with commutators of the linearized field string. And along with that is a function that gives a short distance singularity. I made a lot of noise about the absence of short distance singularities at 4 points, but they clearly come in at 5 points. So you can define this short distance singularity function G as follows. You start with a prime form. You take the logarithmic derivative of the prime form, and then you strip off an abelian differential. So this gives a 1 form in Zi, and now some derivative of Jacobi theta function with respect to the coordinate zeta in the Jacobian. So what do we have? It's the logarithm of some odd spin structure theta function. And yeah, these zetas I defined for you before. So this is essentially an integral from Zi to Zj of the 2-component vector of the omegas. All right. Now here, this is something that may trigger a question. Which of the odd spin structures should I use? There are 6 choices at genus 2, and term by term, it matters. They are not the same if I use one spin structure or the other. But the good news is the composition in the chiral amplitude. I mean, there are many such G's in the chiral amplitude, and their precise composition is such that the choice doesn't matter. And there's even more stuff that cancels. The experts may remember that the prime form involves so-called half differentials. They are needed to make it independent on the choice of odd spin structure. And these half differentials cancel, not in the individual ones, also not in this line, but as we go through the rest of the chiral amplitude and assemble everything. So I'm making a kind of spurious choice term by term, but we also have amplitude representations in our paper where this choice is manifestly washed out. So this is maybe another price to pay if you want to have things the chirally split way. It can be beneficial to allow such spurious new dependence in intermediate stages. Okay, but if you're easygoing about these subtleties, just think about this G as being a simple pole. So the tree-level version of that G is just a simple pole, 1 over Zi minus Zj. So this is also what you get from an OPE. Good. This took us through the first line. Then the second line has to do with loop momentum. Right, I made a big deal about the loop momentum dependence. Now here is almost the loop momentum. This calligraphic P is a kind of dressed version of the loop momentum, dotted into a polarization vector of leg 1 and decorated with T8 tensors of the others. And it comes with a bit of combinatorics. Okay, so what is this dressed loop momentum, as I lovingly referred to it? Is green readable? Sometimes green is infamous to not go well on Zoom.
It's fainter, but we can read.
Okay. Yeah, it's essentially the loop momentum per se, but also it brings some external momenta as reinforcement. So this is J different from 1 with external momentum. And now once more, this little g function, which is to zeroth approximation, the short distance singularity 1 over Zi minus Cj. Okay, so you see there are a lot of g's sprinkled over the two lines, and they combine in such a way that the choice of odd spin structure drops out, or that you get the same result for either of the 6 choices. All right, then this is finishing the recycling part. As I highlighted before, a substantial part of the chiral amplitude is the genus 1 result, dressed by some 5 form. But this is not the full story. There's also a term that doesn't have an immediate genus 1 counterpart. It still fits into the remaining 2 lines of the blackboard, but it's something which is harder to smell or predict. Okay, so here is the rest of the answer. K1 dotted into this dressed loop momentum at Z1. And here I now need a bit of combinatorics. Forms. And some T8 tensors here of a commutator again of field strengths. Also some explicit epsilon.k polarizations dotted into momenta, and T8 with the remaining linearized field strengths. Okay, and now we need permutations 2 versus 3, 3 versus 4. And finally, and now I see my blackboard management break, we need to add cyclic permutations. Oops, I'm sorry that this is poorly readable now. It's the term that I wrote in the last 2 lines, plus 6 some cyclic permutations in 1, 2, 3, 4, 5. Okay, and how come that there is now a less intuitive term without any genus 1 counterpart? Well, if you were to place this object at genus 1, then you would get 0, at least after integrating over the vertex points. So this becomes total derivative at genus 1. And it therefore would integrate to 0 if we were on the genus 1 curve. So it can't have a genus 1 counterpart, or, well, a putative genus 1 counterpart is 0. Okay, so this is on the one hand completing the 5-point chiral amplitude, but also concluding my 90 minutes. So maybe I'll just go for another 2 minutes to make a few comments, if this is okay.
Yeah, that's fine.
Okay, so now this was the parity even part for external bosons. And the parity odd part can also be written down nicely. The parity odd counterpart is the same 5-form combination upstairs together with the Levi-Civita symbol. So the parity odd term would simply add here some epsilon 10 with insertions of the loop momentum, epsilon 1, and otherwise linearized field strengths. It's the same tensor structure that is already there at 1 loop 5 points in the parity odd part. But also with this is just the external Lewis-Schwartz states. And in the first of the 3 papers from the beginning, June 2020, with Eric, Boris, and Carlos, we also have a pure spinor representation where the polarization dependence resides in superfields, pure spinor superspace, and where the expression is constructed from BRST invariance, locality, double periodicity. So in chiral splitting, you don't see it manifestly that the correlators are periodic on the Riemann surface, but you need some extra constraints to see the double periodicity, interlocking the loop momenta with the loop momentum independent terms. So you can even view it as a virtue, as some information for a bootstrap program to get chiral amplitudes from information on the double periodicity, which is not manifest term by term. But yeah, in short, you can look up a superspace version of this correlator with all the Raman sector states encoded. Then what else do I want to add? Yeah, the low energy expansion has also been investigated in one of the papers. And in order to do so, we have integrated out the loop momenta and obtained manifestly modular representations, where, for instance, the prime form hidden in the Cobra-Nielsen factor here is promoted to be the closed string Green's function. More precisely, the Arakelov Green's function on the genus 2 surface, which is most friendly to do the alpha prime expansion and to integrate over the moduli order by order. Yeah, now it's really time to stop. Sorry for going over time, and yeah, thanks a lot.
Thank you very much, Oliver. Over time, there was nothing because we started a bit later, so you're completely spot on time. Okay, thank you very much for this nice exposition on the current state of these amplitudes in superstring. I would like to ask if there's any question from the audience.
I have a question.
Yeah, Beatrice.
Hi, Oliver. So what happens? So if you translate an external state around an A cycle, and these chiral blocks, they remain invariant, right? If I remember correctly, is that true?
On the A cycle, yes, but not
Yes.
so on the B cycle.
Yes, on the A cycle. Yes. Okay, good. So in these loops, you have NS states and also Raman states. So I was wondering what happens if you factorize on a Raman state, because then you would expect this period somehow the fact that it's a Raman state will manifest in some different periodicity for the translating state around this.
Yeah, I fully agree. Yeah, that should be isolatable. The method I would try.
Is it clear?
Oh, sorry, there was an instability on the connection.
Yes, but now I can hear you.
Okay, yeah. So I would try the RNS formalism at a fixed spin structure, where, well, there are 10 even spin structures that are responsible for the parity even part. Let's focus on parity even for simplicity. And a goal could be to simplify the chiral amplitude at fixed spin structure before summing over the 10.
Mm.
Then you can really disentangle what is the contribution of the GSO projected Neville-Schwarz sector and what's the separate contribution of the Ramond sector. And yeah, that's heavily in progress.
Okay.
It has to do with looking at the Sego kernels, the fermionic two-point function in the RNS formalism, and to check how it depends on the spin structure.
Mm.
To unwind the spin structure dependence from the functions of the external vertex points from the Zs.
Mhm.
So at one loop, this is under good control. There, the Sego kernels can be disentangled to any multiplicity. Say that the spin structure dependence can be disentangled from elliptic functions in multiple variables. And yeah, in this way, we know at one loop how to isolate the Ramond sector and the endpoint function. And it's mandatory to do the same for 2 loops and ideally beyond.
Okay, great, great. Thanks.
Okay, are there any other questions? Well, if not, I'd like to thank Oliver again. Sorry, it seems like I lost the video.
Oh, I can still hear and see you.
Oh, okay, sorry. So we just so I'd like to thank you again, Oliver, on behalf of the organizers and we will come back in 2 weeks, the last seminar of the semester by Hiroshi Kunitomo.
Yeah, thank you so much for having me and everybody for being rewarding audience. Take care, stay safe.
Okay, thank you. Bye-bye.
Bye.